All right. And we are live. Yes, we are live. Oh, you crazy kids. Yeah. I'm imagining that when I go live for a video, that there's a cheer that rings out across all of Barnegat. People just clapping and chanting, and I don't know. There's a lot of noise. Whatever. It just does its thing. But it seems like there's only 6 of you so far. That's weird, considering that there's like 20 something kids in the class. I don't even know. Oh, that's 7. Number slowly going up. So I'll stall a little bit just to let people kind of get into the live stream, to give you guys heads up as to what's going to be happening in the next week or so. By the end of next week, we should be wrapping up this chapter. And in wrapping up this chapter, there is going to be a major assessment. Now, I am not going to assign that major assessment until probably the middle of next week, Tuesday or Wednesday or something along those lines. But I am going to be assigning that assessment. It's going to be great. It's going to be fantastic, mainly for me. My goal for today is to begin reviewing certain concepts. Now, I kind of want to do like an overall-ish type thing today, with some various problems that I have in mind, including some graphing problems, which graphing is the main focus, because you do have something due from me. I got to check the due date on that. You do have something due for me tomorrow by 2 o'clock. So please keep that in mind. You have something due for me tomorrow at 2 o'clock. And there are very specific directions that are involved with that. So please make sure you are reading that carefully. Let me see if anyone's actually turned it in yet. One person has turned it in. Okay, I'll check that later. But again, I just want to make sure that you guys are aware that that assessment is there, and that I will be checking them soon. Anywho's, it's so. As I was speaking, the number only went up to like 9 or something like that. But yeah, it is still morning, isn't it? It's like 9:30 in the morning. My word, that's crazy. Anyway, so what I would like to do, I would like for those notebooks to be out and open. Ladies and gentlemen, last class we spent most of our time working on a quizzes. And that quizzes was designed to give me a bit of insight. The insight was involved around what do we know, what do we not know. And it was very important to me that we did that. Now, I specifically chose those questions because I knew that a lot of those questions were going to have some weird notation and that we may not be doing very well with it. But we were going to do the best we could. I'll flip that to here. Come on, wrong thing. There we go. Boom, boom. There we go. Now I'm just going to bring up the chat on my phone because with me sitting at my desk, I would prefer to see if anyone has any questions while I'm going through with this. Here we go. All right. So I have that there. That's ready to go. And let's start with this. Now, like I said, this is meant to be a little bit of a review-ish type day, considering the major assessment that I have for you guys next week. But let's just see where it takes us. So let's just call this polynomial practice. Today is the 3rd. There we go. Let's see where we're at. Now, first problem that I would like to do, I would like to go all out on this problem. I would like to graph it. but of course finding all of the important information that is involved with it. So the problem that I have in mind is f of x equals x cubed minus x squared minus 4x plus 4. Now our ultimate goal is to graph this thing, but I want to go all out on this problem. I want to go all out on this problem. And what I mean by that, by going all out on this problem, I want to not only factor it, I want to find the solutions, I want to get that table of values, I want to graph this thing, and I want to find the end behavior or be able to describe the end behavior. That's what I want with this problem. And I will get what I want with this problem. The first thing that typically should be done or could be done is throwing this equation into your graphing calculator. Now, obviously, if you have Desmos, you have Desmos. I'll actually show you both real quick. Let me bring up Desmos here. There we go. Desmos. Come on. There we go. F of x is equal to x to the third power minus x to the second power minus 4x plus 4. And this is the equation that we get. Now, obviously, it's a bit easier to see on Desmos, especially with it being red on the screen and stuff like that. But you can get some finer details that you might not be able to get on the graphing calculator. Of course, you can throw this into the graphing calculator if you wanted to. What's really nice about it is that this thing actually does identify the exact x-intercepts, which, again, we're going to use those on paper in a little bit. You'll see. What's really cool about Desmos is they actually also identify the turning points. No, I'm not going to actually click these because they're decimal values, and I really don't want to mess with them right now. When you're graphing, you're just going to estimate approximately where these turning points take place based on the table of values. But with this thing, with Desmos, you can get the exact value, which is really nice. I don't know. What? Sorry. I just saw there was a comment from Johnny Beasley's videos. That's weird. I don't know what that is. Anyway, back to this. Click. If I were looking at the graphing calculator, I'm going to zoom in right there. Zoom. Focus. I can graph that thing, and you can see approximately what that looks like. And then you could visibly estimate where those zeros would be. So it looks like +2, +1, -2. And of course, Desmos can confirm that for you. But I need to see some more information. So I need to prove it. I would like to prove that those zeros are what they say they are. So in order to do that, start with a little synthetic. 1, -1, -4, +4. Okay. Those are my coefficients. I'm gonna do the +2. The +2. Just for funsies. 1 plus nothing is 1. Multiply, add, multiply, add, multiply, add. Nailed it. Now, again, I want you to recognize what you have done here, because this is part of the process that we've been doing in this chapter. I want you to recognize what you've done here. You have taken a cubic equation. You have taken a third-degree cubic equation. Boom. And you have used synthetic division to divide out one of the factors. Now, 2 is the zero that you have divided out. X minus 2 is the factor that you have divided out. But look what you have left over. Remainder, constant, x squared. That's what you have left over. You have a quadratic left over. Now, I'm going to take a slightly different track on this problem. Considering the fact that we have a quadratic, you have options. Your options, if you had that quadratic, would be to continue with more synthetic, You could do the quad formula if you wanted to, although I'm not going to with this problem. Or, in the case that I'm going to do, I'm a factor. This is an x squared plus x minus 2. That's what we have there. It is an x squared plus x minus 2. All right. I'm a factor that. If I were to factor that problem using everything that we've done with the Tucker method of factoring, I would end up with something like this. 2 times -1, 2 plus -1, it works. Or with whatever factoring method you know how to do with that problem. Now, we can't just leave it like this. We need to be able to label and identify various things. So first, let's identify the factors that we have found. The factors, or the factorization of this problem, or if the problem just said, hey, factor completely, there's our x plus 2, there's our x minus 1 down here at the bottom. But those are not our only factors. We still have this number right here. We proved that this number was indeed a 0 of the function. You can see where I'm pointing there. We proved that positive 2 was indeed a 0 of the function. Thus, x minus 2 is a factor. It's kind of nice. It's kind of nice. Now, those are the factors. If we had to factor completely, those would be our factors. What about the zeros? Well, the solutions, the x-intercepts of this particular problem, we end up with something like this. -2, +1, +2. Yay! Whatever. Okay. Now, that wasn't the ultimate goal of this problem. I said the ultimate goal was we were going to eventually graph this thing. But now we know where the zeros are. Now we know that it's factored completely. We also know that there are no repeated zeros and there are no complex zeros. Let's talk about how we know that. He's here. Let's talk about how we know this. Let's talk about how we know there are no repeated zeros and no complex zeros. We found 3 real zeros in this function. We found 3 real zeros, 3 actual x-intercepts. What is the degree of the polynomial? The degree of the polynomial is 3. By all of the definitions that we have covered in the past, by all the definitions, if the degree is 3, then according to definitions, we would have at most 3 real zeros. Well, we found exactly 3. There can't be any more. There can't be any more than that if the degree is 3. If you include repeated and complex solutions, this is the other definition that I have given you. If you include repeated and complex, then we should have exactly 3. How do we know that the degree was 3? Good question. The largest exponent in the equation. The largest exponent. Whatever the largest exponent is, as long as you have a polynomial, of course, polynomials, the only exponents that a polynomial has are positive whole numbers. If you have a polynomial, the degree of the polynomial is the largest exponent that you have. So if the degree is 3, you should have exactly 3 solutions if you include complex and repeated. But since we already have 3, there clearly aren't any complex, and there clearly aren't any repeated. Now, I am going to do a problem today where we will see either a repeated or complex solution. I'm going to talk about that. But let's move on with this problem, because we're still doing this problem. I still have to finish this problem. It's the same problem that we've been doing over and over and over again. Anyway. Okay. I'm going to need a table of values. I already typed this thing into my y equals key earlier. That's how I was able to look at it. You can see it right there in the y equals key. Once you have that equation in the y equals key, second graph will take you to this screen. Second graph. Now, yes, I can visibly see what that end behavior is on the graph, but I want to write down some of these numbers. Now, ooh, -4, -60. Yikes, I'm not typing. I'm not writing down those numbers. I think I'm going to start with -3, -20. So let me write down some of this information here. I'm going to write down, in terms of an XY plan, I'm going to start with -3, -20. And then I'm just going to keep writing down what I see on this thing. Let's see, -2, 0, -1, 6, 0, 4. I'll zoom out a little. You can see what I'm writing there. There we go. And I'll repeat these, of course. 1, 0, 2, 0. Let's go a little farther. Ooh, 3, 10. I can definitely plot that. Ooh, and then 436. Ooh. Yeah, I'm not going to write beyond that. I know what's going to happen. Let me repeat these numbers here. I wrote down -3, -20. I wrote down -2, 0, which we knew -2 was 0. -1, 6. 0, 4 is your y-intercept. 1, 0, and 2, 0 are the other two zeros that we found. 3, 10, which I'm definitely going to plot that one. And 436, I'm not going to plot that. See, here's the deal. If you look at the graph and you can visibly identify what the end behavior is supposed to be, you can see that to the left, this thing is going down forever. It's going to go down to some large negative numbers. Going to the left on the table of values, you can see I've already reached -3, -20. Oh, I'm not going to go any farther than that because it's just going to keep going down. It's not going to come back up. Ms. Markey, how do you know it's not going to come back up? I'll tell you why. In a minute. To the right, this thing is going up. Positive infinity, 3, 10, 4, 36. Ooh, those numbers are getting bigger and bigger. It's going to keep going up forever. It's not going to come back down. Mr. Markey, how do you know it's not going to come back down? I can tell you exactly how I know it's not going to come back down. First of all, there's two reasons how I know that those end behaviors are not going to change. Number one, that is the end behavior of the actual graph. It is a third-degree polynomial, odd. The leading coefficient of the problem is a +1 because the number in front of the x cubed is a +1. The leading coefficient is the number in front of the variable with the degree. Since it is an odd degree, opposite directions, and since the leading coefficient is positive, then this is what the end behavior should resemble to the way far right and to the way far left. That's one reason how I know that these curves are not going to come back around. The other reason why I know is because of the number of turning points. We have a definition written from last week or the week before, I can't remember, where we basically said if the degree is n, then the polynomial will have at most n minus 1 turning points. Meaning if the degree of this polynomial is 3, then it should have at most 2 turning points. And that's exactly what's going on here. Let me get rid of this. I'm going to zoom into my calculator so we can see those turning points. I know exactly what this thing is doing. Zoom in. No, zoom in. Here we go. Woohoo. A turning point is a change in vertical direction. This thing's going up, 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 up. Turning point, down, 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 down. Turning point, up, 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 up. It's already hit the accurate number of turning points. Since it's already hit 2 turning points, by definition of the degree and turning points, it can't have any more. It could have less. It might have 0 turning points. I mean, there is a way to draw these with no turning points. Like there's one with no turning points right there. You can't see it, the glare's in the way, whatever. Which you may end up having something like that. It doesn't have to have turning points. But we know that this one has hit the approximate limit. So let's graph the sucker. Chapow, chapeau. I'm not going to plot -3, -20. I'm not going to bother with -3, -20 because it's too far. But I'm going to plot that. -2, 0. -1, 6. 2, 3, 4, 5, 6. 0, 4. 1, 0. 2, 0. 3, 10. 7, 8, 9. Hilarious joke, and 10. All right. I'm not going to plot 436. But with these points, I can draw this thing out. Now, you're not just connecting the dots. You have to have a smooth curve. Thing's going to come up and back down. Now, again, down here, you're not going to have a horizontal line. Smooth curve. End behavior to the right. End behavior to the left. That is what this graph looks like. That is how you're going to be able to identify all this stuff. End behavior. As x approaches infinity, meaning as it goes to the right, f of x approaches infinity, meaning it goes up. As x goes to the right, it goes up. That's literally what I just wrote. As x goes to the left, as x approaches negative infinity, the function goes down. It also approaches negative infinity. That is that end behavior. Woo! End behavior. Excellent. Excellent, excellent, excellent. Now, again, like I said, this whole day, this whole class period, I am deep diving these problems, and I'm going a bit farther than what we have been used to. So I'm finding my next problem that I would like to do. Oh, that's a fun one. No, we'll save that one for another time. Oh, I love these problems so much. Okay. Solve that one for that one. I want to get one with a very specific answer. Very, very specific answer. And I guess that's going to have to be it. Okay, here we go. I want to make sure that this one's done correctly. Okay. And okay. Just give me one moment and I got this. Got him. Okay, here we go. Next page. I had to make sure that this example worked out the way that I wanted it to. X to the fourth minus 5x squared minus 36. There it is. Cool. So I'm looking at this thing. X to the fourth minus 5x squared minus 36. And I have to solve this thing completely. I have to graph this thing completely. I better look at what this looks like. So hold on. Let me type this into my y equals key. I'm looking at the y equals key. Oh, goodness gracious. Okay. Let's take a look at this. Look at what we got here, ladies and gentlemen. Oh, my word. It's just literally two straight lines. I'm not going to end up just drawing two straight lines. I got to do something else with this. Now, some people might panic at this point. Be like, okay, I got to zoom out. Let's zoom out. Oh, what is going on down there? What's going on down there? I don't know. Let me zoom back in down there. That's what it's doing down there. Oh my gosh, we're going to have to make some concessions with how we draw this thing. All right. Eventually, we're going to have to graph this thing. Eventually. You might get a better view on Desmos. Let's try it on Desmos. X to the fourth minus 5x squared minus 36. Okay. On Desmos, it still has that weird thing with the two lines. Oh my word, it's like an extended W. Ugh, that's so gross. Well, that's what we're doing. That's what we're doing. Let's see what happens. Put my screen back to normal. Visibly, I can see two places that it crosses the x-axis. I can see two places where it crosses the x-axis. Looks like +3, looks like -3. So what does that mean? For us, at least. What does that mean? It looks like it crosses at +3. It looks like it crosses at -3. But it's a 4th degree polynomial. It's a 4th degree polynomial, meaning if you include repeats and complex numbers, if you include them, it should have 4 total solutions. I'm only seeing 2 real ones. That fits the definition because, of course, a 4th degree polynomial would have at most 4 real solutions. That weird looking W does fit the idea of turning points. That weird looking W does fit the idea of turning points because it has 1, 2, 3 turning points. A 4th degree polynomial could have at most 3 turning points. Oh, this thing is so weird. And it's missing things. It's missing an x cubed, and it's missing an x. Oh my gosh. How are we ever supposed to do this? How are we ever supposed to factor this thing down as best we can? How are we supposed to solve this thing? Oh my gosh. Here's what we're going to do. We can visibly identify 2 of the zeros. We are going to use synthetic division, and we are going to divide out the 2 zeros that we can see, and we are going to whittle down this 4th degree polynomial down to a quadratic. Because once we get it down to a quadratic, we have options. Let's see what we can do here. It looked like +3 and -3. I'm pretty confident on that. But in order to find the other solutions of this problem, we are going to have to take them out. Let's just see what happens. I'm going to create a synthetic bar. Now, keep in mind, I'm missing the x cubed, and I'm missing the x, which means that if I am going to fill out the synthetic bar correctly, notice that I had put zeros in as placeholders. Notice that I put zeros in as placeholders. You have to do that in order for this to work correctly. We'll start with the +3. Doesn't matter which one you start with. Let's see. 1 plus nothing, multiply, add, multiply, add, multiply, add, multiply. Oh, that's positive. Add. It worked. Now, note what you have. I'm not going to write the equation out, but note what you have. Just kind of mentally note what you have here. This is your remainder, your constant, your x squared, your x cubed. That's what you have left over. You took a 4th degree polynomial and you whittled it down to a 3rd degree polynomial. But we need to keep going with synthetic division. And we have an additional 0 to divide out of this thing, thankfully. So I'm going to divide out a -3 as a 0. But notice in the synthetic bar, notice the numbers that I am using, because I don't want to go back to the original. If I go back to the original, I'm not going to get anywhere. I whittled it down to a cubic. I got to whittle it down farther to a quadratic. So let's keep going. 1 plus nothing, multiply, add, multiply, add, multiply, add. It worked. Notice what we have left over now. At the bottom of the screen, you have your remainder, which is this 0. You have your constant. You have your x. Yes, that's 0x. And you have your x squared. We have our quadratic. Once you get it down to a quadratic, you have options. But only if you get it down to a quadratic. Let's see what's going on here. We have an x squared plus 4. And that's what we're trying to solve. Fun fact, you can't factor it. You can't factor that. That one right, I can't even point, right there. You can't factor that. You could try to factor it. You could try. Can you think of two numbers that multiply to 4 and add up to 0? Because there's no such thing. You can't do it. If you were to look at the graph for x squared plus 4, if you were to look at the graph for x squared plus 4, notice what I see. This is x squared plus 4. That's x squared plus 4 right there. It doesn't have any x-intercepts. Now, we still have to find the solutions. But keep in mind that x squared plus 4, since it is not factorable, it is one of our factors. Factors. X squared plus 4. Look where I'm pointing. X minus 3. Look where I'm pointing. X plus 3. Those are our factors. That's all we can do in terms of factors. Now, real solutions, and notice I'm emphasizing the word real solutions, we got 3 and negative 3. Oh, happy day. But we have to go a bit farther now. We have to go a little bit farther. And what we have to go farther with is finding the other two solutions. See, the thing is, there are no repeated solutions for this particular problem. How I know that is because the turning points do not occur on the x-axis. Last class, I gave you a definition which basically stated that you would have repeated solutions if the turning point occurred on the x-axis, which none of these turning points do for this problem. They occur way down below. Weird. But if we don't have any repeated solutions, then where are the other two solutions coming from? The other two solutions are complex. The other two solutions are unfortunately named imaginary. Stuff that we covered with quadratics. And we are going to be able to find them. And we're going to be able to find them from this quadratic. What we're going to do is we are going to take that quadratic and we are going to shove it inside of the quadratic formula. This is x squared plus 0x plus 4. And we are going to shove that thing inside of the quadratic formula. This is stuff that we did last chapter. If I were to take the a, b, and c and put them inside for the discriminant, I would get negative 16. And a negative discriminant, as we learned last chapter, a negative discriminant produces complex solutions. So, negative b plus or minus the square root of negative 16, the whole thing is over 2 times a. Now, what I have always taught you, about taking the square root of a negative is that when you take the square root of a negative, that negative produces I. It produces the complex number I, the square root of -1. You could break that up to be the square root of -1, the square root of 16, which would become 4I. Another way of actually doing that is by changing the mode in your calculator. You could change the mode in your calculator here. Where if we go to mode and we change it from real to A plus BI, all of a sudden, now I can take the square root of -16. That's stuff that we did last chapter. So what this becomes, plus or minus 4I over 2, which becomes plus or minus 2I. So, solutions. Solutions to this problem. We had 3, -3, 2I, and -2I. There are your 4 solutions. There are your 4 solutions. I'm going to bypass graphing this one for now. I really just wanted to solve that one. I mean, we could graph it if we wanted to, but the numbers are incredibly large. But those are the 4 solutions. If you include repeated and complex, the number of solutions you get will be equal to the degree of the polynomial. There it is. I love it so much. I love it so much. Oh, this problem. Now, there actually is a really interesting definition in regards to complex solutions, but I'm going to bypass that for now for the sake of trying some more of these problems, just because I love it so much. Okay. Ooh, that's a good one. Let's try that one. I have a different problem for you to try. So we have the problem, example, divide x cubed minus 2x squared minus 9 divided by x minus 3. Now, this is something that we do need a little bit of practice on. Of course, like I said, today is just meant to be a bit more reviewish type thing than anything else. But I just want to make sure that we're going back and hitting these kind of finer points. Now, I just ask for you to divide it. That's all I'm asking for you to do with this problem. Hey, divide these two. Well, looks like synthetic division to the rescue. Looks like synthetic division to me. So let's do that. What goes on the inside? Well, in order, I have to put these numbers. Mr. Markey, where did the 0 come from? The 0 came from that missing term. Came from that missing term of 0x. What do I put on the outside? Now, this is where a lot of people ended up messing up on the most recent minor. A lot of people ended up putting a -3. Oh, no. X minus 3 is the factor. Positive 3 is the potential 0 that you put out there. You don't put -3 as the factor. You put the k value, which is x minus k, which in this case would be x minus 3. 3 is what you put out there. Now, all I said was divide. Will it work? Will it not work? I don't know. Just see what happens. 1, 3, 1, 3, 3, 9, 0. Hey, it worked. I honestly had no idea that it was going to work, but it worked. It worked nonetheless. kind of messed up. I'm going to show you something in the calculator in a moment, but we'll see. It's going to be great. But what we have left over here, we have a remainder, a constant, an x, and an x squared. So what do I write as my answer? That's the big question. What do I write as my answer? Do I have to find all the zeros? Do I just have to factor it completely? Do I have to graph it? What do I have to do? All this problem wanted you to do is divide. That's what the directions say. Hey, divide. Give me the result of the division. The result is 1x squared plus 1x plus 3. That's all that problem wanted from you. See, the biggest issue that students are going to have over the course of this chapter is that they're going to try to do either too much or too little. And this is some of the issues that I saw on the homework that you guys did for me on the previous page. Some of you weren't doing enough, or some of you were doing too much. And I was trying to leave feedback on various assignments just so that we were all on the same page. I was trying to leave feedback, trying to get them graded as quickly as possible too. We have to recognize what the directions are actually asking of us to do. It really depends. Let me show you something on the graphing calculator real quick. This is actually with this problem, with this exact problem, because I find it very interesting. Just how everything relates to one another. So if I go to my graphing calculator and I type in x cubed minus 2x squared minus 9, I just want to look at that graph real quick. Look at the graph. Whee! Now, it looks weird. I know. It looks very weird. It looks like it only has one real solution. It looks like there's something going on with like turning points down here. I'm not really sure what the heck's going on there. But it looks like it only has one real solution. Strange. Look what I can do in the y equals key. I find this fascinating. Look at this. In the y equals key, I can take this polynomial in parentheses and divide it by that x minus 3. I can literally divide it by that x minus 3. Now, mind you, of course, you have to put that original polynomial in parentheses along with the x minus 3 in parentheses as well. But look at the resulting graph right here. This is unbelievable. Look at the resulting graph right here. When I take that division, I get a quadratic. Now, that should make sense. I took a cubic. I divided it by one of its zeros. It results in a quadratic. I'm whittling it down. But that exact quadratic, and this is actually really cool that you can do these things on the graphing calculator. I can take the quadratic that we found. 3, yeah. Plus 3. There's the resulting quadratic that we found. Now check this out. Some people know how to do this, but you can actually change the style of line by moving it over to the left and just kind of clicking on it and changing it. I'll move that up a little bit. There we go. So you can see that a little better. So basically, when I graph it, it's going to have the original, and then it's going to graph the quadratic right on top. Whee! It's really messed up. It just proves that it is what it says it is. I could also do something like this. I don't know if you guys know how to do this kind of thing. Not that. That. Here comes the quadratic, and here comes the second one. Whee! It's just a line or a circle. I don't know. It's very strange. But yeah, everything depends on what they're asking of you. Let me give you another example. And again, it depends on what they're asking of you. New example. Solve 5x cubed equals 30x minus 25x squared. New problem, new issues. Miss Markey, what am I supposed to do with this one? Am I supposed to graph it? Am I supposed to do synthetic division? What do you want me to do with this problem? I want you to solve it. How do I do that? Well, let's think about what we have. And let's think about what we can do with it. Most of these problems that I've been throwing out at you, most of these problems, I ask you to look at the graph. Because if we can look at the graph, if we can identify some x-intercepts, we may be able to divide them out using synthetic division. Okay, sounds weird. With this problem, I'm looking at this problem. There's one glaring issue that I have with this problem. And the glaring issue that I have with this problem is the fact that it's not equal to 0. I got to get it equal to 0. This goes back to the beginning of the year. The beginning of the year with quadratics. If we were going to solve a problem like this, we needed to get one side of the equation equal to 0. Because getting one side of the equation equal to 0 will allow so many different opportunities in solving this problem. So let's move this crap over to the other side. 5x cubed plus 25x squared minus 30x equals 0. Now we're in better shape. We're in better shape right now. Much better shape. If you wanted to, at this exact moment, you could look at the graph. Now, I'm going to show you the graph, but I'm going to caution you to don't panic. Let's just put it that way. Let's look at the graph. See, by looking at the graph, we might be able to visibly identify any x-intercepts that we may want to divide out of this thing. Let's just see what happens. Graph. Oh, gross. Oh, so gross. Oh, again, I told you, don't panic. Don't panic. I'm not asking you to graph this thing. The problem clearly stated, hey, solve. We are simply looking at the graph to see if we can visibly identify any x-intercepts that may help us in our work. I definitely see 2. There's something weird going on here, but I definitely at least see 2 of them. That may be helpful. Now, something that you also need to recognize. Something that you also need to recognize from the equation. Let me go to my y equals key real quick. This is a 5x cubed plus 25x squared minus 30x. There's no constant. There is no constant. That's a bit of an issue if there's no constant. We can account for that. We can account for that constant in synthetic division. We can totally do that. But we do have to account for it. Here's the other thing that you could recognize. And this is actually a little bit of a shortcut. Think back to the very first step of the Tucker method of factoring. The very first step of the Tucker method of factoring was to take out the greatest common factor. 5, 25, and 30 all have a 5 in common. Also, x, they all have an x in common. You could, if you wanted to, take out a greatest common factor of 5x. But just for the sake of argument, let's just pretend Like we didn't see that. So, let's see what we got. I am going to look back at this graph one more time and just hope, okay, it looks like positive 1. Positive 1 looks like a 0. And what? Negative 2, 3, 4, 5, 6. It looks like negative 6. Okay. Looks like positive 1 and negative 6. Let's see if we can't do this. Synthetic bar, 5, 25, negative 30, and yes, you do have to account for it. You do have to account for it. That constant. This was the x cubed, the x squared, the x, and the constant. You have to have that constant. Let's try negative 6. Just because I want to knock out some large numbers here. Let's see. 5, negative 30, negative 5, positive 30, 0, 0, 0. Okay. Huh. I knocked out some big numbers here. This is helpful. Huh. Look what you got. Remainder. Constant. I'm sorry, I lost my train of thought. Remainder, constant, x squared. Wait, is the 25 positive or negative? Good question. The 25 x squared originally started out on the right side of the problem. And in order for me to do this correctly, I had to add it to both sides in order to get one side equal to 0. See, because originally here was our equal sign. I needed to move these two terms over to the left. So I had to subtract the 30x and add the 25x squared in order to get one side equal to 0. And once I got that one side equal to 0, 5, 25, negative 30, and the constant being 0, I needed to throw those into the synthetic division. Now look what you have left over here. Look what you have left over here. Remainder, constant, x squared. You have a 5x squared minus 5x. You have a quadratic. So, again, at this point, you have options. Once you get it down to a quadratic, I mean, right now, you could take out the greatest common factor. Right now, you could totally take out the greatest common factor if you wanted to. Or we could continue with synthetic. It's completely up to you what we do. Now that we have the quadratic, I'm actually going to utilize my quadratic skills. And I'm going to factor out a GCF of 5x. Factored. Now, I still have to solve it. Mind you, I still have to solve it. But it's factored. I just took out a GCF and now it's factored. 5x equals 0. X minus 1 equals 0. I set each term equal to 0. Equals 0. Equals 0. X equals 0. X equals 1. And according to the synthetic division that we just did, x equals negative 6. Notice, I didn't ask you to graph it. I asked you to solve it. Looking at the graph is how we begin attempting to solve these things, by looking at the graph. By looking at the graph, you can visibly identify zeros that you could then divide out using synthetic division. Now, the rest of the graph didn't really help. Kind of did. I knew positive 1 was a 0. I had no idea what the graph was supposed to look like. But by looking at the graph and seeing those lines, if you can visibly identify any x-intercepts, then you can start with synthetic division. Of course, I had to get one side equal to 0 first, but that is just the common rule that we need to do and that we have been doing since the beginning of the year. Now, again, there is a worksheet that you guys have to do for me that is due tomorrow that is focused on graphing. It is focused on graphing. I reviewed a little bit of graphing this morning, and I reviewed a bunch of other stuff as well, clearly. Next week, probably Tuesday or Wednesday, I am going to assign you the major in regards to this chapter. If you have any questions, of course, you can email me. I'm going to be wrapping up the next couple of minutes. If you have any questions, of course, you can email me. But of course, on Monday, I'm going to continue reviewing various topics from this chapter. Various topics. And it's going to keep bouncing back and forth between graphing and solving and factoring and all this other stuff. But a lot of it is going to boil down to, look at the graph. Can you visibly identify things? Where can you go from there? How do you know how to divide by -6 when you did the synthetic division? Good question. Well, where did I get the -6 from? Where did I get the -6 from? Once I got one side equal to 0, I threw that equation, I'll move the calculator in a moment, I threw that equation into my y equals key. I had to get one side equal to 0, but then I threw that equation into my y equals key. Now, I did say before I graphed it, hey, don't panic. I'm not asking you to graph this, but watch very carefully. I'm going to hit graph in a moment. I want you guys to watch very carefully how this thing moves. Look at it move. Boom, boom, boom. Like I said, don't panic on where it is, but let's look and see if we can't visibly identify any x-intercepts. This is where I got the -6 from. 1, 2, 3, 4, 5, -6. I believed that -6 was one of the zeros of the function. That's where I started. Like I said, visibly identifying them on the graph, that's the key. My bell is going to ring right here, right about... The bell should have rang. There it is. That thing is off. Anyway, I do apologize. I'm out of time. You got to move on to fourth period. I'm going to sign off in a moment. But like I said, if you have any questions, additional questions, email me. I do have various things that I have to get done in the second half of the school day or the afternoon in regards to my department and creating various things. I don't know. I got this light on my forehead. Can you see that? That's kind of cool. I don't know. Cool. Anyway, see you guys. Have a good day. Take your stuff from underneath your desks. Goodbye.